Hi and welcome back to Properties and Structures of Matter, Module 1, and we're looking today at Inquiry Question 4, all to do with bonding. Now we've talked about in our previous video looking at electronegativity, and we're now going to see a different way that we can show that sharing or transfer of electrons through our drawing of electron dot diagrams. Now, obviously, our covalent bonds are a sharing of electrons. Our ionic bonds are a transfer of electrons. And the idea here is they all want to achieve that noble gas or inert gas status, which is that of a full outer shell. So we can see in the example here we have neon sitting here with the electron configuration of 2,8. It has that noble gas status. Now in the next one here we have fluorine, which has the electron configuration of 2,7. So there is one electron in the outside shell missing to gain that complete outer shell. Now if we look at sodium on the far right here, it has one extra electron and its electron affinity, electronegativity is quite small. We saw that in the previous example. Its electronegativity, I think, was about 0.9 thereabouts. And say, for example, here our fluorine is probably in excess of 3.5. So there is a huge a difference in electronegativity. So it's going to form an ionic bond, and fluorine is going to take that electron from our sodium there. So the hold of electrons is far greater, and that desire, the affinity for electrons, is far greater with our fluorine. So what is going to happen is this one electron is going to transfer across into our fluorine there, and it's going to gain the electron configuration then of 2,8, as is this one here. The difference is, though, they still have 9 protons and 11 protons in their nucleus, so they still have the same properties of the element that they initially started at, again due to the protons that we have. But as this one here has gained an electron, it is going to become charged, and it's going to have a 1 minus charge, and this one is also going to become charged because it has lost an electron, and it's going to have a +1 charge. So one way of representing this a little bit clearer is in the use of Lewis dot diagrams. So before I do a couple of examples, we'll go through a couple of the rules that apply or that can help us draw these diagrams. So the first thing we're going to do, first of all, is look, we're only looking at the valence shell electrons. They're the ones that are really involved in the reactivity there, and so we're only really looking at those. It gets a little bit messy with all the different shells, so we're just going to look at those outside ones. So the first thing we need to do is look at how many valence electrons I have in each element. And we're going to draw that in a series of dots around the element, hence the name Lewis dot structures. Then we're going to decide how many electrons does it need to gain, or how many does it need to lose. So using that knowledge that we already have about ionic and covalent bonds, we're going to then start thinking, is it going to be an ionic bond that is forming or a covalent bond? If it's an ionic bond, then we are actually transferring electrons. How many electrons are going to be lost? How many electrons are going to be gained? And we're going to draw the symbols then with the electrons having already been transferred, and then put a charge on it so that we know that that has actually occurred. Or for a covalent compound, we work out how many do we need to share to gain that noble gas configuration, and we pair up our electrons. So let's have a look at a couple. This one here is for our ionic compounds, and we have, for example, our sodium atom reacting with our chlorine atom. I just might move this one up and over a bit. So our sodium atom, you can see here that we have 1 electron in its outside shell just there. And we represent that with one single dot. Sometimes we might do it in a different color. In the case here, it's red. Sometimes we do it as a cross, and there's still a bit of conjecture about what's right and what's not, as long as what you do is clear. So we have one electron in the outside shell, and chlorine has 7. So you can see here we've got 7 electrons around that outside shell. It needs 1 electron. Sodium needs to get rid of 1 electron, or rather chlorine has a greater affinity for that electron, so it will pull that electron off. Now, the way we're going to write that is that 1 electron here is going to transfer into that space just there. So now sodium has no electron in that outside shell. It's gained that outside shell, so we write it here with that positive charge. Chlorine, on the other hand, has gained that 1 electron, and it is obvious here with that electron just in here. And we write them in square brackets. Okay, that's indicating that it is a ionic bond. And again, we have that negative charge there saying how many electrons were gained there. Magnesium is the same. We can see in this case, however, there are 2 electrons in the outside shell that it is going to take, but conveniently, oxygen requires 2, that you can see in the 2 gaps there, so those 2 go across. If, however, you look at calcium with fluorine, calcium has 2 electrons in its outside shell, but fluorine only has 1 electron short, so we're going to require 2 of those. So in this case, calcium is going to lose both its electrons, 1 to one fluorine atom, 1 to another fluorine atom. Again, we still write it with the charge, calcium 2+, still the square brackets, but this time there are 2 of them. So what happens with our covalent compounds? Well, these guys are sharing them rather than transferring them. So in this case, we don't have our square brackets around them, but we can see in our first step how many electrons are in its outside shell. So in its outside shell here, you can see that there are 7 electrons and 7 electrons. Each one of them need 1. Now, neither one of them are going to want to give away those electrons. They're wanting to gain 1 each. So the best thing that they can do is share them. So we write them there together with our valence electrons around the outside. We bring them together and we can see here that they are sharing that electron each, and that is where our bond actually occurs. So where those 2 electrons are shared is where the bond occurs. Again, a whole heap of practice in class. See you then.